Hi, everyone. Again, I am really sorry that I cannot be with you. I feel like a lot of this stuff would be easier if I was just with you and I could explain in person. So, what I want to do in this video, literally, I want to read through. You should think of these as class notes. I'm going to read through these things. I'm going to highlight certain things that I want you to really focus on. I know there are a lot of words here, but this would be as if I was with you and we were talking about this in class. It is really important that you follow what we're doing. I got the impression from the sub teachers that that you guys were having trouble with this, and it's really important to me that you understand this. And I just want to walk you through this now. All right, so first thing on here, I want you to really take note here. This was in a previous video. You really should think of what we're doing right now as review. Right now, we are reviewing Unit 3. And in fact, as we're doing this right now, today, we are in fact also reviewing certain aspects of Units 1 and 2, because in this class, everything is building on everything else. And this Unit 3, builds directly on top of what we've already done in class. So anyway, what I'm saying here is that this was in a previous video, so I'm reviewing this with you right now, that energy can do two things. Okay, in this unit, we're talking a lot about energy. Energy can be transferred, and energy can be stored. Okay, when we get to the LOL diagrams part of this, we're going to be explicitly looking at what energy is being transferred and how is the energy being stored in our system. Okay. All right, and then also I just want you to know that this word phases, we're using that word to describe solids and liquids and gases. So those are the three phases of matter that we're concerned with in this class. So when you hear that word phases, that's what I'm talking about. I'm talking about solids and liquids and gases. We started out this unit by looking at the icy hot demo. Okay, I call it the icy hot demo. What you saw was solid ice being melted and then heated up, and then that water boiled. Okay, so I'm literally going to be reading through this worksheet so that you're following point by point what I wanted you to see, what I wanted you to learn, and what I want you to understand about what we're doing right now. Okay, so in this demo, we saw that we took a beaker, a large beaker of solid ice, and we added heat to it. Okay, we put it on a hot plate, we added heat to it. Heat was being transferred into that solid ice when we started this demo. Okay, now as the heat from the hot plate passed into the ice began to melt. All right, now this is a really important point. Take a look at the screen right now. Okay, before we did this demo, before we did this icy hot demo, you predicted, everybody predicted in class, hopefully you remember, we made this prediction that we said, well, if at time 0, and if we start adding heat to this system, then the temperature should just go up, right? Adding heat causes temperature to go up. Adding heat causes temperature to go up, and so on. Okay? But we did not see that. We were adding heat all the way during this process, okay? In fact, the people that were sitting close to that hot plate could feel the heat radiating off of that hot plate. There was a lot of heat going into that system. It was going into that solid ice. But during that time, there was no temperature change. It took a long time before we started seeing a change in temperature, okay? All right, so In part A of this graph, throughout part A, energy was transferred into the ice, but the temperature did not change. Remember what temperature is. Temperature is the speed of particles. Okay? In all previous observations before this one, temperature always increased when we added energy, and that's what we would have predicted, but our prediction was not, confirmed. At first, the temperature did not change as we were adding heat. The speed of the particles were not changing as we were adding heat. So if temperature is not going up, if the speed of the particles is not increasing with increased heat, then what the heck is going on? What is happening here? Okay, that's the new part, the thing that is unique about part 3. I'm sorry, unit 3. Unit 3 in our course, all right? One of the things that is very unique that we're seeing now, the new thing that we're seeing, is that temperature doesn't necessarily change when there's a change in energy, okay? So what was happening? For the answer, we need to think back to Unit 1. Now remember, Unit 1, there was a difference between solids and liquids and gases, right? Those are the phases of matter. And we found that the densities were different for these things. Solids had more density, generally, mostly, usually. Solids have more density than liquids. Okay, liquids are slightly less dense than solids. And when we were dealing with gases, we found that gases were incredibly low in density, like thousands and thousands times less dense than liquid and gas. Okay? So what was going on there? Okay? The densities implied that there was a difference in the spacing of particles. Okay? Now, I've got this diagram right here, and I want you to see how in the solid particles, the particles are all packed together. All right? So, when a solid has a certain temperature, the particles are in motion, but they're moving by vibrating. They're just vibrating back and forth. They're not moving around, they're just vibrating back and forth. With a liquid, we've got a slightly separated, or the particles are slightly separated from each other, just slightly. And now these particles are able to move around each other. That's the characteristic of a liquid. Particles are moving around each other, but they're not separated very much. Okay? With the gas, they were way, way low in density. Okay? So now we're showing that particles are separated by a lot. In fact, if I was to draw this particle diagram, I would have made these particles even farther away from each other, because this gas is thousands and thousands of times less dense than this liquid. All right? In other words, particles are separated by a lot. Okay? Now you can imagine, for that separation to happen, that would take a lot of energy. Okay? We're going to come back to this. Okay, so again, we saw, and this is in part A of the graph that's above, right? In part A, we saw that temperature was not increasing, okay? So what does this have to do with melting ice and the fact that the temperature didn't change? The answer is this, okay? This is what you need to get out of this. The added heat that went into part A of that graph wasn't causing the particles to move faster. The heat was causing the particles to separate, okay? And that is the energy of phase, okay? It takes energy to make those particles separate like that, okay? So now the particles aren't changing speed with the added energy. They are being separated from each other with the added energy. That's the big deal. You have to focus on that right now. That is the big idea here in this unit, okay? Energy, by the way, is being stored. As energy is being transferred into those particles, we're not increasing in the ETH. We're not increasing in the thermal energy. Now we're increasing in phase energy. Okay, phase, because we're changing phase now. We're going to be going from a solid phase to a liquid phase. There's an energy, a phase energy change here. Okay, so I want you to focus on this highlighted part here. During a phase change, adding or taking away heat energy does not cause a temperature change. Okay? During a phase change, particles are being rearranged. They're being separated, okay? That's what I mean by being rearranged, okay? The energy that goes into rearranging or separating those particles in this way is called phase energy, okay? This is stored energy. Remember, everything that you're looking at right now is meant to be kept in your notes, and you can add notes to anything that you're seeing here. I say this every time that we do this, okay? Okay, let's talk about part B now. In part B of this graph, this is more typical, right? We're adding heat energy as we go along, and as we're adding heat energy, the temperature is increasing. You know, that's not really surprising. The surprising part was with the phase changes, okay? All right, so now I'm just focusing on some of the things that I wrote here. Let's talk about the thermal energy, okay? A lot of you had questions, I think, yesterday about what is thermal energy. Guys, this was all in a previous video which you were supposed to watch, and if you didn't ever hear the words thermal energy or ETH, it shows that you did not watch the video. Anyway, beyond that, let's move on. Okay, so as heat is transferred into the liquid water, the temperature increases. In other words, the particles are moving faster and faster. The motion of those particles, the particles moving around, that is thermal energy, and we're calling it ETH, okay? During part 3, the transferred energy, right, from the hot plate is being stored as thermal energy, ETH. Throughout part B of this graph, the particles just stay slightly separated from each other. This process continues until we reach 100 degrees Celsius, which is called the boiling point of water, okay? It is the temperature at which water boils. Okay, let's continue here. We're on part C now of this graph. At the very beginning of part C of the graph, we have all liquid water at 100 degrees Celsius. So let's be clear about what was happening in part B. Okay, remember, just review. We started at 0 degrees Celsius and the temperature climbed all the way to 100 degrees Celsius. Take a look at your graph. I'm not projecting it right now, but you can look at the graph and you can see that we went from 0 degrees Celsius to 100 degrees Celsius as we were adding heat. Now, here we are in part C, where at the very beginning we have all liquid water, and that liquid water is at 100 degrees Celsius. All right, at that very instant that we hit 100 degrees Celsius, we start boiling water, okay? And at this point, the heat is transferred into the water. The temperature, again, does not change, all right? So if you refer back to that part C in the graph, you can see that we're adding heat energy all that time in part C, and there is no temperature change. The temperature stays at 100 degrees Celsius, regardless if we turn up the temperature on the hot plate or turn down the temperature on the hot plate. It doesn't matter, okay? It doesn't matter how much heat energy we're adding at this point. As long as we're at 100 degrees Celsius, we've got boiling happening. If we add more energy to that, the boiling is going to happen faster. It's not going to increase the temperature at all. All right, so at this point, as heat is transferred into the water, the temperature again does not change. The transferred energy is now causing the particles to separate from each other. Again, added energy is being stored in the rearrangement of the particles. Okay, this again is phase energy. Okay, and in this time, and here I'll just read this. The particles of gases are much more separated than they were as liquids, very much more separated. It takes a lot of energy to make that happen. It takes a lot of energy to separate those particles. I'm just going to give you an analogy. Just listen carefully. If you were to get up right now and try to lift your desk off of the floor, right? If you were to try to separate your desk from the floor right now, that would take energy, right? In fact, some of you might not have enough energy to actually lift the desk, right? The higher you lift the desk, the more energy it takes to lift it. Think back to what you learned about gravity last year in physics. You lift something off of the ground and it increases in gravitational energy. Well, this is exactly the same thing, all right? The more you separate those particles of water, the more EPH you have, the more phase energy you have. Okay, so if you're ever confused by this, think back to what you learned about gravitational energy last year. Okay? Okay, so bottom line, it takes a lot of energy to separate particles. So let's talk now about these LOL diagrams really quickly. Since we're looking at an LOL diagram right now, before we start this, just look at the LOL diagram right now as I'm speaking. I'm going to use my laser pointer. ETH and pH and ECH are all ways in which energy can be stored. Okay? We are not going to deal with ECH in this chemistry class. Okay? We're just never going to get to chemical energy like that. Okay? At some point in your education, you will probably take chemistry again in college, and you'll learn about chemical energy. All right, for right now, for our class, we're only concerning ourselves with ETH, thermal energy, and EPH, phase energy. All right, we're going to work with an LOL diagram, and every time we work with this LOL diagram, the initial conditions are on the left side, the final conditions are on the right side, and this circle represents the system that we're dealing with, okay? And this has got to do with energy flow, the transfer of energy, okay? Again, energy can be stored, energy can be transferred, and that is what the LOL diagram is showing us, or going to show us. All right, these are the rules that we're going to follow when we're putting together an LOL diagram, okay? All right, here it is. To show temperature, ETH, thermal energy, okay, we are going to use 1 bar to show cold temperatures, below room temperature. 2 bars will be used for temperatures that are at about room temperature, like about 20 degrees Celsius or so. 3 bars will be for like really hot stuff, like hot to the touch, right? So that would be, let's say, around 70 or 100 degrees Celsius. And 4 bars of energy is just going to be really hot, okay? All right, guys, there's nothing like that particular about this. We're going to just stick with these rules. Let's not, overthink temperatures too much. We're just trying to show where energy is going and where it's being stored. Okay? All right, I'm not going to go to the next page, but you can go to the next page. Look at EPH and look at the rules that we're going to follow there. Okay? We're always going to give solids 1 bar. Okay, so if we're dealing with EPH of a solid, that's always going to be 1 bar of energy. If we're dealing with liquids, we're going to give that EPH value a value of 2 bars. Okay, for liquids. There's never going to be a situation where I'm going to use 3 bars for EPH. All right, we're going to jump to 4 bars though. Why 4 bars? Remember, it takes a lot of energy to go from a solid to a gas, or from a liquid to a gas. It takes a lot of energy. So we're going to use 4 bars of energy to show that there's a lot of energy being stored, or a lot of energy required for that phase. All right, so I'm going to work through this. Follow what I'm doing as I'm doing it, and you can do the same on your paper right now. Okay, so we're starting we started our demo. If I'm thinking about the icy hot demo right now. We started the demo at 0 degrees Celsius. Okay, and we had solid ice. So 0 degrees Celsius is 1 bar of thermal energy. Solid ice is 1 bar, representing EPH, a solid. Okay, 1 bar for a solid. All right, where did we end up? Okay, in the end, we ended up with gas. Okay, now gas, EPH, is 4 bars. I'm just following the rules that we just established. And the temperature is at boiling. Okay, so in the end, we were boiling water, ETH. All right, so we were adding a lot of energy during this entire process. So we transferred energy into the system. How much energy? Well, we're starting with 1, 2 blocks, and we're ending with 1, 2, 3, 4, 5, 6, 7, 8 blocks. Well, that means we're adding 6 blocks of energy into our system. And I'm just going to draw that right now. 6 blocks of energy. That's going to be like a lot of energy. Okay. Okay. 1, 2, 3, 4, 5, 6 blocks of energy going into that system. Okay. And that's all there is to it. I'm not asking a whole lot when I'm asking for LOL diagrams. I just want to see what were the initial conditions of how the energy was being stored. What are the final conditions about how the energy is being stored? And what kind of energy flow was required to make that happen? Did we add energy? If we added energy, how much energy? How many blocks of energy? If we took energy out, how many blocks of energy did it take in order to get from initial to final? That's as much as you need to think about it, but it is a really great way to inventory energy. Okay? Okay, guys, so that's it. I want you to keep all of this in your notes. Okay? The purpose of this entire video was just to really clarify some misunderstandings. And I also realized that many of you didn't watch the previous videos, so I really needed to explain this, and I needed you to be treating this as if it were a class lecture where I was with you, okay? So I'm going to leave it at that. Thanks, everyone.